Hello, welcome everybody. In this video, we're continuing chapter 10 and talking about some coupling reactions with alkyl halides, and then we'll talk a little bit about oxidation and reduction. Okay, so the two types of reactions we'll be focusing on are Grignard reactions using Grignard reagents, and then other organometallic coupling reactions. And then again, the overview of oxidation and reduction. Okay, so what is a Grignard reagent? This is actually something really powerful that is going to create a carbanion, basically a carbon with a negative charge that can go on and do some other reactivity. The way that you make it is you take an alkyl halide and you react it with a neutral magnesium. So this is a redox reaction that occurs. Magnesium is oxidized. And basically for you guys, just think of magnesium slipping right here in between the R group or carbon and the halogen, the X group. So the X is one of these halogens here, chlorine, bromine, or iodine. And what you get out is this R group, your carbon containing alkyl group, magnesium, and an X. So magnesium is a group 2 metal. Think of it as a 2+ here. X is a 1-. So overall, this is 1+. So think of your carbon as a 1-. So here we're showing a bond. So this carbon has this partial negative, partial positive on the magnesium end. But really, the way that you want to think about Grignard reagents is that it's a carbanion, and the Mgx part is just the cation portion of that. More specifically, I can show this with iodomethane reacting with magnesium, which is typically done in ether. You have the magnesium slipping in here, creating your Grignard reagent. This carbon is then anionic. And it's basic and nucleophilic. So depending on the situation, it can add in and attack something positive. A lot of times it'll act as a base and just pull off an H off of some other compound. Okay, so here's your carbon center, again, more negative, and then magnesium and iodide here. What can you do with a Grignard? Basically, one of the simplest things you could do is convert an alkyl halide to an alkane. There are sometimes we need to do this or want to do this. As chemists, sometimes we have a bromine or some other halogen there that was a handle, or maybe it was there and we don't want it there anymore. So what we can do is overall take an alkyl bromide and convert it to an alkane, where the bromine is converted to an H. So the way we do that, it's pretty straightforward. Add your magnesium to form your Grignard reagent. And then this carbon, then think of it again as a carbanion. It has this negative charge. So if water is present, it'll just pull off the H off of water, leaving hydroxide, generating the alkane. Okay, so the carbanion is a very, very strong base. That's why it's going to deprotonate water. Let me take you back to our acid section. The pKa of an alkane is in the 50 range. So that's very high on our list of pKa's. Water is much lower. It has a pK of 15. That means water is more acidic. It'll want to give up its H more. Higher pKa wants to hold on to its H. So in this reaction where you have a C- here, water is going to act as an acid and give up its H, and you'll generate your alkane product. Okay, something else you can do with halides is basically prepare other types of organometallic compounds. So one is a lithium compound, the other is further modifying that to give a copper compound. And these are both powerful in their own way. Let me just focus on the lithium one first. So if you just take, say, 1-bromobutane, this alkyl bromide, you can react that with lithium. So don't worry about the amount of lithium. I just want you to know that you're reacting with lithium to form this N-butyl lithium, the straight chain. So in this case, it's very, very similar to the Grignard reaction or Grignard reagent, where the lithium is a plus, and that means your carbon here is a minus. So again, think of this as a carbanion where your carbon here is very basic and nucleophilic because it is attached to this Li+. The reactions are going to be very similar to Grignard reagents. You can treat that with water. The other thing you could actually do is treat it with an isotope of water, so deuterium, so D2O, and you could actually label different types of alkyl groups with a D, this isotope of H, which has its own uses to track molecules or just study reactions and reaction mechanisms. Another more useful preparation of organometallic compound is converting that lithium reagent into a lithium diorganocopper reagent. So basically what you can do is take two organolithium compounds. So let's just use methyl lithium here. React it with copper iodide. So this is copper 1+. This is typically done in ether, and you can generate this lithium dimethyl copper. We call this a Gilman reagent. So don't let this look complex to you, because we could just really break it down. This basically is saying you have two methyls that are anionic. So these two carbanions here, that's a total of 2-. Copper is a 1+. So this whole thing is a 1-, balancing out with a lithium 1+. The one thing that you really need to know is that the carbons are bonded here to copper, and you have two of them. Generally, we're delivering one, but they're anionic. The reason why this is more useful is because being attached to copper, it makes it a little bit what we call softer. So it can do different types of reactions, and it ends up reacting a little bit better with other alkyl halides to form carbon-carbon bonds. So that's what you could do with Gilman reagents. It's extremely powerful. Making carbon-carbon bonds is one of the most important things you could do in organic synthesis, because it's tricky to do. A lot of the synthetic reactions that you want to carry out need to come together through carbon-carbon bond reactions. A lot of the CO bonds or NC bonds or halogen C bonds, those are easier to make. The carbon-carbon ones are harder. So these are really prized reactions. They're really just really valued. A lot of the Nobel Prizes in chemistry go to some carbon-carbon bond forming reactions. Okay, let me just show you what we can do. We basically used a Gilman reagent to couple some alkyl group with another alkyl group. So we use this copper reagent, or Gilman reagent. Again, it shows that it has two methyls, but we're effectively just going to deliver one of those methyls, and that methyl is a nucleophile. And so just look at this and think, oh, CH3-. If you have an electrophile, remember we said that carbon is electropositive next to halogen. So if you have an electrophile, it'll want to attack that carbon center, that partial positive carbon center. So the negative methyl will come in and attack this carbon center, and it's a coupling reaction. So I'm not showing a clear mechanism here, but basically you're going via this copper reagent, and in the end what you get is a new carbon-carbon bond between that carbon that was attached to the I and the methyl group that was on the Gilman reagent. So look at that. I can make whatever Gilman reagent I want, whatever type of alkyl group here. I can come in with whatever alkyl iodide I want, and I can make and stitch together a variety of different new hydrocarbons. Something else that's powerful is you can use the Gilman reagent on even aryl or alkenyl iodides. And so you can transfer a methyl to this sp2 center and form this methyl substituted benzene, which is given the name toluene. That's why it's so powerful. Okay, so you guys practice here. Provide the reagents to carry out the following transformation. So we're starting with a straight up, just very basic cyclohexene. and we are going to install a methyl group. Just notice that I showed you how to form a carbon-carbon bond, but you do need some sort of handle. So how would you form that here? So pause this, think about it, take your time, and unpause and I'll go over it. Okay, so again, you're gonna make a carbon-carbon bond here. You know how to do that using the Gilman reagent. So you've got to form that Gilman reagent and then add in this group. That's the easiest thing to do. Make the Gilman reagent, this group, and then add in this group. So to do that, you need a handle here. And to put a handle in, you can install a bromine. How do you do that? That's an allylic position. So then start thinking radical chemistry. Specifically NBS, light, carbon tetrachloride, can generate a radical in this position. And then you can generate the lithium reagent, the alkyl lithium compound, treat it with copper iodide and ether to generate the Gilman reagent. And again, Gilman reagent just has 2 of those, but still you're just delivering 1 of those. Think of these are 2 anionic groups. And then this anionic carbon here will form a bond with this methyl group in methyl iodide. So those are your main steps to carry that out. Okay. The last little bit is just giving you an overview of oxidation and reduction. We've done a lot of different types of reactions, and it's just good to just step back and see overall, okay, what's happening. So oxidation and reduction in organic chemistry is a little bit different in definition than what you learned in general chemistry. So for us, our focus is carbon. For an oxidation, it's when carbon loses electron density. So how does it do that? For example, you can have a CH bond and that bond breaks and forms a bond with something more electronegative. Why does it lose electron density in that? It's because here, a CH bond, there's very little difference in electronegativity, so there's no bond dipole. But here, chlorine, for example, is very electronegative relative to carbon. So there's a bond dipole, so that chlorine is pulling electron density from the carbon. So there, that's your oxidation. You're going from, this carbon is losing electron density because it's being pulled from this chlorine. So again, oxidation is when you break a CH bond and you form, say, a carbon O, carbon N, or carbon X bond, because those are going to be more electronegative and withdraw electron density. A reduction is the opposite. So basically, say you start with a CCl bond and you go to a CH bond. In that case, carbon gains electron density. So you're going to break this bond. Here we're actually forming a Grignard reagent and then protonating the resulting carbanion to give this methane product. You break that CCl bond and you form a CH bond. So this is a reduction. So just be able to identify those. Here's a range for you. The highest oxidation level is here where carbon has more electron withdrawing groups, basically. So CCl4, CO2 is on this end of the spectrum. On the other end is where carbon has as many hydrogens as it can. So alkanes will have the highest number. Here, as you increase oxidation levels, they still have a fair amount of hydrogens, but still they're introducing more electronegative groups. As you keep going, you have a lot more electronegative groups. Here, 3 chlorines. This carboxylic acid has a CO double bond and a CO bond. Here you have 3 bonds to nitrogen. Okay, and just finally, we're going to practice with just one in terms of identifying, is this transformation an oxidation, reduction, or neither? So what you want to focus on is overall for the molecule. When you carry out a hydroboration and subsequent oxidation with peroxide and sodium hydroxide, converting the bromine to OH, what happens? Basically, you add H and B across the double bond and the B is converted to O. So overall, it kind of looks like an oxidation, right? Why don't you guys just pause and take a minute and think about this? So overall, it looks like an oxidation, but don't forget, when you did the hydroboration, you added H here. You added HB across the double bond. So you added an H and an O. So it's kind of like one oxidation occurred and one reduction. So they kind of cancel each other out. So this would be in the neither category. Okay, that's where I want to end, and we will chat more later.